Part 1. The Discovery of the Impossible Glow. The early hours of November 10, 2025, marked a turning point in the history of modern astronomy. During a routine stretch of night-long observation, the scientists monitoring our star detected something that shattered every expectation. An intense, sharply defined blue radiance was rising from the empty space near the sun. The luminosity was strong enough to slice through protective filters specifically designed to soften the sun's overwhelming glare, and its vivid hue resisted all explanations grounded in established principles of stellar physics. The first moments were filled with absolute bewilderment. Solar monitoring centers across the planet plunged into a level of confusion they had never faced before. That deep blue radiance bore no resemblance to any solar phenomenon ever documented. It was not a conventional solar flare whose radiation tips toward ultraviolet and X-ray wavelengths. It was not a coronal mass ejection either, which typically drives waves of expanding plasma observable across many bands. This light was something else, a concentrated crystalline blue, so uniform in tone it felt more like the output of advanced technology than the work of any natural process. Computerized early warning systems began issuing urgent notifications to researchers on 3 continents. Emergency procedures intended for extreme solar events activated briefly, until experts realized that what they were witnessing did not match any known pattern of solar storms. The sheer power of the glow suggested an immense energy source, yet its location in space did not correspond to any active solar region. By midday, 14 independent solar observation facilities had verified the anomaly. Each one reported the same impossible event: a compact source of intense blue light positioned in the space surrounding the sun, clearly separate from the solar corona itself. Initial positional measurements placed the source roughly 0.3 astronomical units from the sun, exactly in the region where orbital calculations had predicted that 3I Atlas would be passing through its point of closest approach. The timing eliminated the possibility of coincidence. The interstellar visitor, with its enigmatic hexagonal geometry, was now displaying behavior unlike anything previously recorded. A luminous emission no comet or asteroid had ever produced in the entire history of observational astronomy. Comets generate shining comet made of gas and dust that merely reflect sunlight. Asteroids simply return the light that hits them, producing no significant emission of their own, but this was fundamentally different. It was an active release of blue light with an intensity comparable to that of distant stars. The first energy analyses arrived before sunset, and the numbers were unsettling. To produce that level of brightness, 3I Atlas would need an energy output similar to that of a compact nuclear facility. Solar radiation alone could not account for such luminosity, unless some unknown conversion mechanism were operating, one that contradicted every known physical property of cometary materials. The blue glow demanded an immediate explanation, yet no conventional theory offered a convincing one. The emergence of the azure light automatically triggered the early warning systems created to protect Earth's technological infrastructure from catastrophic solar events. Within minutes, space weather prediction centers in the United States, Europe, and Japan received critical alerts from their monitoring algorithms. The systems interpreted the anomaly as a potential precursor to an extreme geomagnetic storm, capable of overwhelming electrical grids and destroying satellites in orbit. Space weather specialists initiated standard protocols for top-category events. Airlines received advisories directing them to reroute their polar flights, where increased radiation levels can pose risks to passengers and crews. Satellite operators shifted their fleets into protective configurations, disabling non-essential systems and adjusting solar panel orientation to minimize exposure. Electrical grid operators activated emergency response plans designed to manage inductive loads that could saturate transformers during high-intensity geomagnetic disturbances. Yet the incoming data contained contradictions. Solar wind measurements showed absolutely normal conditions, a calm stream of charged particles emanating from the sun without notable disturbances. Magnetometers in near-Earth orbit detected no compression of Earth's magnetic field and no unusual fluctuations. X-ray and extreme ultraviolet sensors registered no increases in high-energy solar radiation. Every traditional indicator of dangerous solar activity remained at its usual baseline. The confusion deepened when preliminary spectroscopic results arrived from observatories equipped with high-resolution spectrographs. The blue radiance displayed an emission spectrum completely incompatible with solar plasma. Solar storms generate characteristic emission lines from iron, helium, and other ionized elements at millions of degrees. The blue glow, by contrast, exhibited a nearly monochromatic spectrum, concentrated in a narrow band around 450 nanometers, deep blue visible light. By mid-afternoon on November 10, emergency protocol coordinators began canceling the alerts. The evidence clearly showed that this was not a solar event, despite its apparent proximity to the sun. The source of the blue light posed no direct threat to Earth in terms of radiation or energetic particles. There was no imminent danger to technology or infrastructure. Satellites could resume normal operations, and airlines restored their polar routes without added concern. But ending the alerts did nothing to resolve the fundamental mystery. If the blue radiance did not originate from the sun, then its source had to be the object passing near it, 3I Atlas. This conclusion raised an even more baffling question. What physical process could allow an interstellar visitor, presumed to be an inert comet of rock and ice, to produce a luminous emission so intense and so unusual that automated systems mistook it for a catastrophic solar event? Detailed spectroscopic analysis revealed something that forced solar physicists to reconsider their most basic assumptions. The blue glow was not only anomalous in intensity, its specific color violated nearly every rule governing how astronomical bodies emit light. The dominant wavelength measured exactly 452 nanometers, a deep blue with no known natural mechanism among comets, asteroids, or any other bodies in the solar system. Natural comets shine through two well-understood mechanisms. First, they reflect sunlight, which means their coloration should approximate the sun's yellowish tone. Second, they emit light when molecules in their comae are excited by solar radiation and release photons at characteristic wavelengths. Ionized water emits red and green. Cyanogen produces blue-green. Carbon monoxide emits in ultraviolet. But no common cometary molecule produces the pure, concentrated blue observed from 3I Atlas. Spectroscopy specialists double-checked their calibrations to rule out instrumental error. Telescopes observed reference stars with well-established spectra to ensure all optical systems were functioning correctly. The reference stars displayed exactly the expected absorption and emission lines. The instruments were flawless. The blue radiance was real, and its spectrum was genuinely anomalous. The spectral width of the emission added yet another layer of mystery. Hot gas produces broadened spectral lines due to the random thermal motion of atoms, an effect known as Doppler broadening. The higher the temperature, the faster the atoms move, and the wider the lines appear. The blue glow of 3I Atlas displayed extraordinarily narrow lines, suggesting extremely low temperatures, or an emission mechanism entirely different from that of ordinary thermal gases. The narrowness of the spectral lines pushed the phenomenon further beyond anything conventional physics could explain. Thermal gases, whether in comets or stars, always show a degree of motion, turbulence, or heating that broadens their spectral signatures. But the emission coming from 3I Atlas appeared almost impossibly sharp, as if produced by a system designed to output a single, precise wavelength. It resembled neither natural fluorescence nor any known chemical excitation. It looked controlled. By late afternoon, astronomers coordinated new observational campaigns. High-resolution telescopes were redirected toward the region near the Sun, despite the risks associated with imaging objects against the overwhelming solar backdrop. Specialized coronagraphs filtered out the Sun's glare, allowing the anomaly's blue radiance to stand out with uncanny clarity. Observers noted that the emission did not fluctuate with the intensity variations of the solar wind or with the rotation of the comet-like object itself. The glow held steady, unblinking, as if powered by an internal engine. More data arrived as Earth's night side brought additional observatories into position. Infrared measurements found no corresponding heat signature, an impossibility for any natural process generating visible light of such power. Even the coldest reflective cometary surfaces warm when illuminated. Yet 3I Atlas, blazing in vivid blue, radiated no detectable thermal energy. Radio telescopes scanned for emissions and found none. If the object was undergoing outgassing or magnetic interactions, the associated radio noise should have been unmistakable. Instead, the silence was total. Scientists tracking the object's trajectory also noticed a subtle peculiarity. The interstellar visitor's path deviated slightly from predictions, not enough to cause alarm, but enough to raise eyebrows. Comets often experience non-gravitational acceleration from jets of sublimating ice, but 3I Atlas showed no signs of such jets. No visible coma, no tail, no heat. Nothing that could explain a measurable change in its motion. Yet the deviation persisted, minute but consistent. As the anomaly grew stranger, multidisciplinary teams were hastily formed. Astrophysicists, plasma physicists, spectroscopists, and orbital dynamicists exchanged real-time data across international channels. Every new calculation reinforced the same conclusion. The blue radiance defied classification. Its wavelength was fixed, its intensity was stable, its origin was spatially precise, and its behavior did not align with any known natural mechanism in the solar system or beyond. Late that night, the first composite images combining visible light, ultraviolet, and infrared data were finalized. They revealed the structure of the source with unprecedented clarity. The object's hexagonal silhouette, already noted in earlier observations, was unmistakable, but now it appeared surrounded by a faint, perfectly symmetrical halo. This halo reflected none of the chaotic asymmetry characteristic of natural cometary activity. There were no jets, plumes, dust trails, or particulate arcs. The symmetry was flawless. Most striking was the realization that the blue radiance originated not from the halo, nor from the object's surface, but from 6 equidistant points located along the inner edges of the hexagon. Each point emitted light at precisely the same wavelength and intensity, coordinated with flawless precision. The pattern suggested a system, coherent, structured, and operating in concert. Nothing in nature produced emission points arranged with such geometric exactness. The discovery ignited a new wave of debate. If the energy output was comparable to that of a small nuclear facility, what could be driving it? Natural bodies do not channel energy through discrete equidistant nodes. Natural bodies do not emit monochromatic light with perfect spectral symmetry. And natural bodies do not maintain stable luminosity at wavelengths uncorrelated with heat. The question deepened. If 3I Atlas was not behaving like a comet, then what was it? Some researchers proposed exotic theoretical mechanisms, quantum coherent crystalline ice, unknown plasma confinement states, or photonic emissions triggered by interstellar radiation not yet understood. Others considered whether the object could host internal cavities acting as resonant chambers. But none of these models explained the stable wavelength, the energy output, or the geometric precision. By dawn on November 11, specialized software produced a temporal analysis of the glow's intensity. The radiance did not fluctuate randomly. It pulsed, at intervals too faint for the human eye to perceive, but unmistakable in the data. The pulses followed a pattern, a mathematical rhythm embedded within the light itself. Not Morse code, not prime number sequences, but something closer to harmonic resonance cycles used in precision engineering. The implications were unsettling. If the radiance was artificial, its purpose was unknown. If it was natural, it represented a physical process never before observed in the universe. Both possibilities were extraordinary. The global astronomical community prepared for a full-spectrum analysis of the pulses, hoping to determine whether they carried structure, meaning, or internal encoding. Instruments in orbit and on Earth began coordinated high-frequency sampling. Plans were drafted for modeling the energy source. Observatories recalibrated to capture higher-resolution spectra. As the first coordinated datasets started to arrive, one fact emerged with complete certainty. The impossible glow was not diminishing. It was intensifying. Part 2. The spectrum that defied physics. The detailed spectral data that arrived over the following hours revealed features that pushed far beyond the boundaries of conventional physics. The extraordinary narrowness of the emission lines suggested a level of coherence in the light normally seen only in artificial sources, such as lasers. In nature, luminous emissions tend to be broad and diffuse because particles move chaotically and produce wide ranges of wavelengths. The blue radiance from 3I Atlas displayed a spectral purity that astrophysicists associated far more with engineered laser systems than with any natural astrophysical process. Temperature estimates derived from the width of the spectral lines produced values entirely inconsistent with any known comet model. If the gas responsible for the emission were in thermal equilibrium, its temperature would need to be below 100 Kelvin to generate lines that narrow. But at such temperatures, cometary gases should be frozen solid, incapable of emitting visible light at all. This fundamental contradiction indicated that the mechanism behind the emission did not involve normal thermal processes in which temperature dictates particle behavior. Astronomers began considering non-thermal emission mechanisms, processes in which light is produced without particles being in thermal equilibrium. Electrical discharges in rarefied gases can create narrow emission lines, similar to the glow of neon lights, but producing such discharges in the vacuum of interplanetary space without any obvious source of strong electric fields posed enormous conceptual challenges. No natural comet generates electric fields powerful enough to produce luminous discharges visible across interplanetary distances. Another theoretical possibility involved resonant fluorescence, in which sunlight of very specific wavelengths excites atomic or molecular transitions, producing emission in distinct colors. But resonant fluorescence requires precise matches between the wavelength of incoming sunlight and the allowed transitions in the excited molecule. The solar spectrum is continuous and yellowish, lacking the narrow features needed to efficiently trigger transitions that would emit the pure blue observed. Plasma physicists suggested more exotic ideas involving non-thermal plasma, where particle velocities do not follow standard Maxwell-Boltzmann distributions. In such plasmas, energetic electron populations can excite certain atomic states without heating the surrounding gas, producing extremely narrow emission lines. But maintaining non-thermal plasma requires a continuous supply of energy through electromagnetic fields or particle beams, mechanisms never seen in natural cometary objects. The absolute intensity of the radiance added further complexity. Luminosity calculations based on apparent brightness and known distance indicated that 3I Atlas was emitting roughly 10 to the 14th watts of visible blue light. For comparison, the total electrical output of human civilization at that time was about 3 times 10 to the 12th watts. The interstellar visitor was generating 30 times more luminous power than the entire planet's electrical production, concentrated entirely in a single color. Natural energy sources available to objects in interplanetary space are extremely limited. Solar radiation at 0.3 astronomical units provides about 11 times the intensity that reaches Earth. An object the estimated size of 3I Atlas, several hundred meters across, would intercept roughly 10 to the 15th watts of sunlight across its cross-section. Converting even a small fraction of that energy into coherent blue light required conversion mechanisms far beyond any known natural process. Comets normally shine with extremely low conversion efficiency. Most of the solar energy they absorb is spent sublimating ice, heating dust, or expanding the coma. Only a tiny fraction, usually less than 1%, becomes emitted visible light. For 3I Atlas to generate its observed luminosity using comet-like processes, it would have needed to capture and convert solar energy with efficiency greater than 10%. Orders of magnitude beyond any known comet. The temporal stability of the radiance added another dimension to the mystery. Throughout the first 24 hours of continuous observation, the intensity of the blue glow remained remarkably constant, varying by less than 5%. This stability contrasted sharply with the chaotic behavior of typical comets, which show significant brightness variation over hours due to rotational jets of sublimation, nucleus fragmentation, and episodic gas release. The consistency suggested a controlled, sustained process rather than chaotic geological activity. Multi-wavelength monitoring revealed another baffling feature, an almost complete absence of emission outside the blue band. Typical comets shine brightly in infrared from heated dust, in ultraviolet from ionized gas, and in radio frequencies from complex molecules in the coma. The spectrum of 3I Atlas showed a dominant peak in blue with minimal contributions elsewhere. Such extreme spectral selectivity had no precedent in natural cometary objects. The infrared cameras of the James Webb Space Telescope, aimed at 3I Atlas during its close solar passage, detected thermal emission consistent with a moderately warm object, around 200 to 300 Kelvin. This temperature matched what one would expect from a rocky or icy body absorbing sunlight at that distance. But the infrared output was several orders of magnitude weaker than the blue radiance, confirming that most of the energy was being channeled specifically into visible blue light rather than dissipating as heat. Ultraviolet observations from specialized satellites also failed to show the usual signatures of an active comet. Missing were the strong ionized oxygen, carbon, and sulfur lines that dominate the ultraviolet spectra of comet exposed to intense solar radiation. Instead, the ultraviolet data showed only a weak, nearly featureless continuum, implying that any gas surrounding 3I Atlas was not being ionized or excited in the way expected for a genuine comet. Radio telescopes found no molecular emissions either. Typical comets exhibit clear radio lines from hydroxyl, OH, hydrogen cyanide, HCN, and methanol. molecular fragments released as complex ices sublimate. For days, highly sensitive radio observatories tracked 3I Atlas, but none of these characteristic lines appeared, even at detection thresholds capable of revealing very modest comet activity. The absence of conventional cometary emissions combined with the intense blue glow created an observational profile with no known parallels. Astronomers were witnessing an object that shone brightly in visible blue light while remaining dark or nearly silent across almost every other wavelength. This selective behavior resembled not a diffuse natural process, but a system directing energy deliberately into a single frequency, as if something were channeling power with purpose. Theorists began exploring models involving organized structures capable of concentrating and converting solar energy into directional luminous output. Proposed concepts included arrays of nanocrystals with specialized optical properties, surfaces coated in fluorescent materials optimized to absorb sunlight and re-emit in blue, or even more exotic systems relying on macroscopic quantum coherent effects. All such models shared one requirement: a level of material organization no natural geological process could produce. Comparisons to human light conversion technologies emerged naturally. Photovoltaic solar panels convert sunlight into electricity with efficiencies around 20 to 30%. Light-emitting diodes convert electricity into visible light with efficiencies as high as 40 to 60%. A combined sunlight to electricity to light system using current human technology could theoretically reach overall efficiencies of 10 to 15%, high enough to account for the luminosity of 3I Atlas if its surface hosted similar devices. This analogy to photovoltaic technology did not go unnoticed. If 3I Atlas were using some mechanism akin to this, absorbing sunlight, converting it into an intermediate form of energy, and emitting coherent blue light, then its surface would require functional structures comparable to engineered energy conversion systems. The question shifted, not whether known natural processes could explain the glow, but what kind of organized material could achieve such performance. Skeptics argued that invoking alien technology was an unwarranted leap from observation to extraordinary speculation. They noted that astronomy is filled with initially mysterious phenomena that eventually received natural explanations. Pulsars, discovered in 1967, seemed so artificial that for a short time they were jokingly labeled LGM, Little Green Men. Later, they were identified as rotating neutron stars. Fast radio bursts, FRBs, first detected in the 21st century, also sparked artificial origin speculation before natural models gained support. But proponents of unconventional hypotheses countered that excessive skepticism can blind science to real possibilities. Natural explanations emerged for pulsars and FRBs because the phenomena fit into existing physics once the correct models were found. The blue glow of 3I Atlas did not fit comfortably into any known physical framework without invoking improbable coincidences or unprecedented processes. In such a case, considering unconventional ideas, including technological origins, was not pseudoscience but legitimate scientific reasoning. The debate intensified when new data from the highest resolution spectrographs arrived, revealing fine structure in the blue spectrum that no one had anticipated. The newly revealed fine structure showed faint subsidiary peaks, sidebands, located at fixed intervals around the dominant 452 nanometer line. These sidebands were extremely weak, just a fraction of a percent of the main intensity, and invisible in earlier, lower precision observations. Their spacing was perfectly regular, matching a harmonic pattern more typical of engineered optical resonators than of any natural molecular or atomic process known in astrophysics. Natural spectral lines can split under strong magnetic fields, the Zeeman effect, or under electric fields, the Stark effect. But these processes produce irregular splitting patterns, dependent on field strength, orientation, and atomic structure. The pattern seen in 3I Atlas was neither random nor irregular. Its spacing was uniform, its symmetry exact, and its distribution stable over time, traits difficult to reconcile with any naturally varying magnetic or electric environment. Computational models ran repeatedly to test whether exotic atomic transitions, unknown molecular structures, or extreme plasma states could reproduce the observed spectrum. None succeeded. Every attempt either produced lines too broad, spacing too irregular, or intensities entirely mismatched with the measured pattern. The simulations consistently failed to replicate the precision seen in the real data. Even more striking, the relative strengths of the sidebands followed a distribution matching a mathematical function frequently used to describe modulated laser systems. In engineered devices, such patterns emerge when a coherent beam interacts with an oscillating field inside a resonant cavity. The resemblance did not prove anything by itself, but it pushed the anomaly further outside the domain of natural astrophysical phenomena. As additional observatories around the world pointed their instruments toward 3I Atlas, the datasets deepened the mystery. Late-night analysis revealed another unexpected feature. The sidebands themselves were not perfectly constant. They oscillated in intensity, in synchronized cycles, as if responding to an underlying modulation pattern. The oscillations were slow, repeating roughly every 90 minutes, and remained precisely in phase across all harmonics. Natural cometary processes do not modulate light with clock-like precision on 90-minute cycles. Rotation of comet nuclei can produce periodic brightness changes, but those effects broaden or distort spectral lines. They do not generate synchronized micro-oscillations at fixed harmonic spacing. The combination of coherence, narrow spectral width, harmonic sidebands, and synchronized modulation placed 3I Atlas into a category no astronomical object had occupied before. It behaved neither like a star, nor a comet, nor a plasma cloud, nor any known form of interstellar debris. The data resembled a signature, structured, stable, and repeating. By the early morning of November 12, an international working group formed spontaneously around the anomaly. Without issuing formal statements, researchers shared data streams, cross-checked calibrations, and debated interpretations in encrypted channels. Some argued vigorously for unknown plasma physics. Others insisted the spectral precision was incompatible with natural processes. A minority, cautious yet direct, raised the possibility that the emission mechanism might involve engineered structures. While the debate continued, the intensity of the blue radiance maintained its steady output. The sideband modulation deepened slightly, becoming more pronounced in the highest resolution measurements. The harmonic spacing remained perfectly fixed. No heating, no cooling, no broadening, only unwavering stability. Shortly before dawn, a final dataset arrived from a high-orbit ultraviolet observatory. While ultraviolet emissions remained extremely faint, the instrument recorded tiny bursts, brief millisecond-long spikes, occurring in perfect synchrony with the 90-minute modulation cycle. These spikes were too short and too faint to influence the visible spectrum, yet their timing matched the sideband oscillations exactly. The implication was clear. Whatever was generating the blue radiance was not static. It was active, varying, pulsing, and exhibiting coordinated, periodic behavior across multiple wavelengths. At that moment, one conclusion emerged across independent teams analyzing the data. Nature did not normally behave this way. Whether the explanation lay in physics not yet discovered or in mechanisms deliberately designed, the spectrum defied every known natural model. The investigation had moved beyond simple classification. The question was no longer what kind of comet 3I Atlas might be. The question was, what kind of system could produce a spectrum that behaved like a controlled, modulated source of coherent blue light, deep in interplanetary space? Part 3. The collapse of natural explanations. The ultra-high-resolution spectrographs installed at elite ground-based observatories began uncovering subtle details that pushed the mystery of the blue radiance from a baffling enigma into a genuinely unsettling anomaly. The dominant emission line at 452 nanometers was not completely smooth and uniform, as earlier observations had suggested. Under maximum resolution analysis, it revealed fine structure composed of multiple components separated by regular intervals of roughly 0.02 nanometers. This multi-line pattern with such perfectly regular spacing had no analog in natural atomic or molecular emissions. Spectral lines in atoms and molecules are determined by the laws of quantum mechanics, with separations that reflect the specific transition energies of each element or compound. These patterns are unique for every chemical substance, molecular fingerprints. The pattern observed in the blue glow matched none of the tens of thousands of substances cataloged in existing spectroscopic databases. Atomic physicists attempted to model exotic molecules or unusually excited electronic states that might produce such a pattern. Complex molecules can indeed generate intricate spectra with many lines, but these still follow predictable rules governed by molecular rotation and vibration. The regular 0.02 nanometer spacing did not correspond to any vibrational or rotational progression calculated for plausible molecules under space conditions. Attempts to fit the observed pattern to any known molecular model failed consistently. A more alarming possibility emerged among theorists. The regular fine structure might not be spectral in origin at all, but temporal. If the emission were being modulated at specific frequencies, switching on and off rapidly, the Doppler effect could imprint artificial spectral features due to the object's motion during the emission cycles. This hypothesis implied that the glow was not continuous but pulsed at extraordinarily high frequencies, possibly millions of times per second. Testing this hypothesis required instruments capable of capturing intensity variations on microsecond timescales. Standard photometric detectors lacked such resolution. However, a handful of observatories possessed fast photometers originally designed to study pulsars and other rapid transient events. These instruments were urgently redirected toward 3I Atlas in hopes of detecting temporal modulation. The results arrived within 48 hours and confirmed the most extraordinary suspicion. The blue radiance was not steady as it had initially appeared. Instead, it pulsed with exact periodicity. The pulse frequency measured precisely 8.33 Hz. Meaning the object brightened and dimmed 8 times per second with clock-like regularity. The amplitude of these pulses was modest, about 15% between maximum and minimum, explaining why conventional observations had not detected the modulation earlier. The temporal precision of the pulses was remarkable. During hours of continuous observation, the 8.33 Hz frequency did not vary measurably, remaining stable to at least 5 decimal places. This stability exceeded many mechanical timekeepers on Earth and rivaled quartz oscillators used in precision electronics. Natural phenomena that generate pulsations, such as variable stars or rotating bodies, typically show fluctuations and drifts due to complex physical processes. The unwavering 8.33 Hz rhythm suggested an extremely precise timing mechanism. The 8.33 Hz period corresponded exactly to a 120 millisecond cycle, a value that several researchers noted aligned with electrical grid frequencies used in some regions. Electrical networks in Europe, Asia, and much of the world operate at 50 Hz, while those in the Americas operate at 60. Some specialized applications use submultiples of these frequencies, and 8.33 Hz is exactly 1/6 of 50 Hz. This numerical coincidence might have been incidental, but it added another layer of discomfort to an already deeply anomalous phenomenon. Astronomers investigated whether the pulses could be explained by rotation. If 3I Atlas rotated every 120 milliseconds with surface regions of varying reflectivity or emissivity, this could create periodic brightness variation. But such rapid rotation posed severe mechanical problems. A rocky body several hundred meters across, spinning 8 times per second, would experience immense centrifugal forces, enough to tear apart any natural material lacking extraordinary structural strength. Mechanical stress calculations showed that typical rocky substances could not survive such rotation speeds without fragmenting. Basalt, one of the strongest common planetary materials, has a tensile strength of roughly 50 megapascals. A 300-meter object rotating at 8.33 Hz would experience stresses exceeding 100 megapascals at its equator, far beyond basalt's capability. Only materials with strength comparable to high-grade steel could maintain structural integrity under such conditions. Moreover, waveform analysis of the pulses revealed characteristics incompatible with simple rotational modulation. Rotational brightness variations typically produce smooth sinusoidal curves as different regions rotate into view. The pulses from 3I Atlas showed sharper transitions, rises and drops occurring within fractions of the pulse period. This temporal profile resembled deliberate electronic modulation more than any geometric effect of rotation. The rotation hypothesis also failed to explain why only the blue emission pulsed, while infrared emission remained effectively constant. If surface regions with different properties rotated in and out of view, both reflected light and thermal emission should pulse correspondingly. The absence of infrared pulsation implied that the modulation targeted the blue light emission process specifically, not the object's geometric visibility. Theorists began exploring alternative pulse generation mechanisms that did not involve physical rotation. One possibility was oscillation within the emission process itself, similar to how lasers can pulse due to internal cavity dynamics. But implementing such a mechanism in a spaceborne object with no obvious optical components posed formidable conceptual challenges. Lasers require resonant cavities with precisely aligned mirrors and carefully prepared gain media, an architecture difficult to reconcile with any natural comet-like body. While researchers debated the pulses, another anomaly emerged from orbital tracking data. Precise astrometric measurements of 3I Atlas over several days revealed subtle but significant deviations from the trajectory dictated solely by gravity. The object was not following the pure hyperbolic orbit expected under solar gravity. The deviations were small, on the order of a few hundred meters in position, but systematic and persistent, not explainable by measurement error. This behavior resembled the non-gravitational forces seen in active comets, which deviate from predicted paths due to the reactive thrust of sublimating gases. This rocket effect is well documented in solar system comets. But the deviations exhibited by 3I Atlas differed from known comet patterns in crucial ways. Cometary non-gravitational forces correlate with gas production, increasing near perihelion when sublimation intensifies, and decreasing farther out when ices remain frozen. The deviations of 3I Atlas followed a different relationship with solar distance. The non-gravitational acceleration did not increase smoothly with proximity to the Sun. Instead, it appeared abruptly, activating when the object reached roughly 0.4 astronomical units from the Sun, precisely when the blue radiance first appeared. Before that point, the object followed a purely gravitational trajectory with no detectable deviation. Afterward, it experienced continuous acceleration, whose direction did not align with the anti-solar vector expected from conventional sublimation. The magnitude of this acceleration was estimated at roughly 0.0001 meters per second squared, modest, but easily detectable with modern astrometric methods. For a comet to generate such acceleration through gas sublimation, it would need to expel around a kilogram of material per second, assuming a nucleus mass of several million kilograms. Yet, spectroscopic observations showed no evidence of gas production at these rates. There were no molecular signatures in the spectra and no visible coma to support the outgassing explanation. Another possibility considered was asymmetric solar radiation pressure. Sunlight exerts a tiny force on objects that absorb or reflect photons. For low-mass objects with large surface areas relative to mass, this pressure can produce measurable orbital effects. But calculations showed that for solar radiation pressure alone to produce the observed acceleration, 3I Atlas would need an extremely low density, lower than aerogel, the lightest solid material created by humans. The idea that 3I Atlas might be an ultra-low density structure had appeared earlier when analyzing its initial interstellar trajectory and reflectivity. Some theorists propose that it could be essentially a solar sail, large, thin, and light, formed either naturally or artificially. The blue radiance and the non-gravitational acceleration offered additional evidence consistent with this hypothesis, though not definitive proof. The direction of the non-gravitational acceleration added yet another layer. If the force resulted purely from solar radiation pressure, it should point directly away from the Sun. Instead, measurements showed a misalignment of about 15 degrees between the acceleration vector and the anti-solar direction. Such misalignment could occur if the object were rotating and its absorbing surfaces were non-uniform, creating transverse thrust components. But explaining the exact magnitude and angle required detailed modeling of the object's shape and surface properties. The astronomical community now faced a suite of observations that resisted coherent explanation through known natural processes: intense blue emission with an anomalous spectrum, precise 8.33 Hz pulsations without a plausible rotational mechanism, non-gravitational orbital behavior without measurable outgassing, and the absence of cometary signatures despite close solar proximity. Each anomaly alone might be explained through special circumstances or exotic natural processes, but taken together, they fundamentally challenged conventional comet physics. The most conservative researchers continued searching for natural explanations, arguing that the statistical rarity of interstellar visitors justified expecting unusual properties. Perhaps 3I Atlas represented a previously unknown class of interstellar object with unique composition or internal structure. Maybe it contained exotic minerals or complex organics with no counterparts in the solar system. Possibly its internal geometry created optical or mechanical effects mimicking artificial behavior without actually being artificial. But for a growing number of scientists, the coincidences were piling up beyond what scientific parsimony could comfortably accommodate. Occam's razor, favoring simpler explanations, was beginning to point in an unsettling direction. Was it simpler to invoke multiple unknown natural processes acting coincidentally, or to consider that 3I Atlas might embody intentional design? The debate shifted sharply when several independent teams completed a new round of spectral decomposition on the 452-nanometer emission line. What emerged challenged even the most open-minded natural models. The line did not merely contain side bands or regular substructure. It carried a deeper pattern, one that repeated at multiple scales, fractal-like, across the entire high-resolution spectrum. This multi-scale repetition appeared in the form of nested harmonic groupings. At the broadest scale, the main line exhibited the 0.02 nanometer spacing already detected. Within each of those components, even smaller subcomponents appeared, separated by exact fractional intervals. And within some of those subcomponents, fainter, even tighter patterns emerged, each with perfect mathematical regularity. No natural atomic or molecular system produces recursive spectral structure. Thermal plasmas smear out fine details. Molecular transitions generate complex but non-repeating clusters. Magnetic fields distort patterns irregularly. But nothing in known astrophysical spectroscopy produces nested harmonic order. The pattern resembled engineered signal encoding, structured information compressed into spectral space. Theorists tested every natural mechanism available: hyperfine splitting, Zeeman and Stark effects across extreme field strengths, rotational vibrational cascades, coherent scattering in unusual crystalline ices, and exotic plasma wave interactions. None produced anything close. At the same time, orbital calculations continued to refine the object's non-gravitational motion. The 15-degree offset in acceleration direction persisted, matching the angle implied by the asymmetry in the blue radiance itself. In other words, the same orientation that produced the coherent emission appeared to dictate the thrust-like acceleration. This correlation was hard to ignore. If the radiation pattern created recoil, much like a photon propulsion system, the acceleration would naturally deviate from the anti-solar direction. The numbers aligned disturbingly well. In parallel, pulse timing specialists analyzed the 8.33 Hz oscillations at the highest temporal resolution. They discovered that the pulses were not perfectly uniform. Each pulse contained tiny sub-pulses, spaced at microsecond intervals. These micropulses formed repeating groups, again exhibiting harmonic relationships identical to those in the spectrum. The glow's timing structure and its wavelength structure were linked. Natural processes rarely couple temporal and spectral patterns with such precision. Stars flicker, plasmas oscillate, materials resonate, but they do not imprint identical mathematical relationships on both time and frequency domains. This unified pattern hinted at a single underlying mechanism shaping both domains, a controlled, coherent system rather than a chaotic natural one. The final blow to conventional explanations arrived when a solar-orbiting probe equipped with a particle detector crossed a region downstream from 3I Atlas's trajectory. For the first time, it detected a faint but measurable flux of photons arriving in phase with the 8.33 Hz cycle, even though the probe was far from the direct line of sight. This indicated that the emission was not simply radiative but directional and structured, with pulsed components propagating in a coherent beam. Nothing about the object behaved like a comet anymore. Not its spectrum, not its pulses, not its motion, not its thermal signature, not its non-gravitational acceleration. Each dataset pointed further from natural mechanisms and closer to something organized. By the evening of November 14, the scientific community reached an uneasy consensus. Natural explanations had not merely become strained, they had collapsed. There was no known astrophysical framework capable of simultaneously producing nested harmonic spectral patterns, precise 8.33 Hz pulses with microstructure, coherent directional emission, thrust-like acceleration correlated with emission geometry, and a total lack of gas, dust, or thermal outgassing. Either 3I Atlas embodied physics not yet known to humanity, or it embodied engineering. Neither possibility was comfortable. In internal forums, encrypted research channels, and late-night teleconferences, scientists no longer asked whether the anomaly was artificial or natural. They asked a different question, one whispered with equal parts caution and awe. If the glow was a mechanism, what was it doing? Part 4. The hexagonal geometry and the hidden code. The link between the pulsating blue radiance and the hexagonal shape of 3I Atlas had not been obvious at first. The earliest observations of the object's geometry came weeks earlier, when it was still far enough from the Sun for telescopes to resolve its outline without solar glare. High-resolution images from the Hubble Space Telescope and several ground-based observatories equipped with adaptive optics revealed an unexpectedly regular silhouette, an almost perfect hexagon when viewed from certain angles. This hexagonal architecture sparked immediate debate. Natural astronomical bodies rarely display precise geometric symmetry. Asteroids tend to be lumpy and uneven, shaped by chaotic collisions and random accretion. Comets are usually elongated or irregular, surviving relics of the early solar system. The hexagonal symmetry of 3I Atlas was statistically improbable if the object had formed through any conventional geological process. Yet, nature does occasionally form hexagons. Ice crystals follow hexagonal patterns because of water's molecular geometry. Basalt columns, like those at the Giant's Causeway in Ireland, take on hexagonal shapes from cooling stresses. Some researchers suggested that 3I Atlas might be a fragment of a larger body where crystallographic or fracturing processes produced the observed symmetry. These explanations, though strained, allowed the object to remain nominally within the natural realm. The blue radiance changed everything. When astronomers carefully aligned the points of peak luminosity with the object's orientation, they found something astonishing. The blue light was not coming from the surface uniformly. It originated specifically from 6 discrete regions located at the vertices of the hexagon. Each corner acted as an independent emitter. The highest resolution images captured by the James Webb Space Telescope during a brief window before the glare became overwhelming confirmed this arrangement. The 6 luminous regions appeared as bright, symmetric points, each separated by roughly 60 degrees around the object's perimeter. The alignment was not approximate or irregular, it was crisply hexagonal, deviating less than 2% from a perfect geometric form. This 6-fold symmetry in emission lined up precisely with the hexagonal outline of the object itself. The correlation between structure and emission strongly suggested functional linkage rather than coincidence. If the object were natural, one would need to explain how geological processes produced both the hexagonal shape and 6 precisely placed light-emitting regions. The odds of such a coincidence bordered on impossible. A far simpler interpretation emerged. The geometry and the emission shared a common origin: intentional design. Temporal analysis of the pulses added another layer. The 6 luminous sources did not pulse at the same time, they fired in sequence. The blue glow peaked at one vertex, faded, and then the next vertex brightened. This rolling activation moved clockwise from one viewing angle, completing a full cycle every 120 milliseconds, matching the global pulsation frequency of 8.33 Hz. Engineers immediately recognized the pattern as a scanning or sweeping sequence, reminiscent of man-made devices that activate elements in rapid order. old cathode ray tube displays raster-scanned an electron beam. Rotating radars sweep their beam around. LED matrices light pixels in controlled sequences. The hexagonal sweep of 3I Atlas echoed these technologies far more closely than any spontaneous natural process. Physicists tried to model natural mechanisms that might produce sequential activation across 6 distinct regions. One idea was that the object rotated while some internal feature, a resonant cavity or volcanic vent, triggered different surface zones as it spun. But this required precise synchrony between interior dynamics and rotation, an improbable alignment without some coordinating mechanism. The perfect timing of the pulses contradicted the inherent variability of natural geological processes. Another striking feature was the precise phase separation. Each vertex reached maximum brightness exactly 20 milliseconds after the previous one. 1/6 of the full period. Such clean division into 6 equal phases suggested deliberate timing, not random fluctuation. Natural clocks, such as rotational periods or oscillation modes, can generate regular rhythms, but coordinating multiple emitters into exact fractional phases requires sophisticated timing control. Electrical engineers pointed out the similarity to polyphase switching systems used in power electronics. 3-phase inverters convert direct current into alternating current by firing switches spaced 120 degrees apart. The system on 3I Atlas appeared to operate as a 6-phase analog with 60-degree separations. Such architectures are deliberately chosen for efficiency and harmonic control. Spectroscopic analysis of each vertex showed that all 6 sources emitted virtually identical blue light, same wavelength, same spectral width, same fine structure. This uniformity suggested standardized construction, or at least extremely precise control of emission conditions. Natural geological sources, volcanic vents, fluorescent minerals, sublimation zones would exhibit chemical variability and thus spectral differences. None were detected. The output power at each vertex was also strikingly consistent. Photometric measurements taken during the pulse cycles showed that every source contributed roughly 1/6 of the total luminosity, with less than 5% variation between them. Such an evenly balanced distribution across 6 identical emitters suggested a system deliberately designed for stability and redundancy. In engineering, this kind of distributed architecture enhances reliability. If one emitter fails, the others can continue functioning with only partial loss of performance. Astronomers began constructing detailed maps of the surface of 3I Atlas during moments when the radiance dipped just enough to reveal structural features beneath. These observations showed that each vertex of the hexagon contained a distinct surface element, a slightly raised or recessed region whose reflectivity differed from its surroundings. All features were similar in scale, measuring roughly 20 to 30 meters across, noticeably smaller than the several hundred-meter span of the object itself. The scale of those vertex features was compelling. A 30-meter structure is comparable to mid-sized buildings or large spacecraft built by humans. It is also precisely the range in which engineered effects dominate over crude geological forces. At that scale, components can be fabricated, assembled, and optimized for specific functions. The alignment between the size of these features and the size range of plausible engineered modules did not go unnoticed. Numerical simulations explored whether a hexagonal arrangement with 6 emitters might offer functional advantages. Optical engineers pointed out that 6 sources arranged around a hexagon could generate interference patterns with useful properties. If the emitters produced coherent light with controlled phase relationships, they could form directional beams through constructive and destructive interference. similar to phased array radar systems. Such a system could redirect light without physically moving any components, enabling thrust vector control or directional communication. Calculations showed that a coherent 6-point array could form beams with angular diversity of about 10 degrees, enough to aim within a stable cone. By modulating the relative phases of the 6 sources, the system could sweep the beam without moving the object at all. This capability would be invaluable for an interstellar craft needing to adjust thrust orientation or aim communications at distant targets while minimizing mechanical motion. The scientific community split. Some researchers saw the geometric and functional correlations as compelling evidence of technological origin. Others insisted that such conclusions were premature and that extraordinary natural scenarios remained possible. Skeptics argued that humans are adept at detecting patterns, even where none exist. Hexagonal symmetry, while rare, does occur in nature. Coordinated pulsations might arise from complex internal resonances. The uniformity of the emitters could be a selection effect. Astronomers notice only the unusual. Supporters of the technological hypothesis responded that excessive skepticism can be as limiting as credulity. When multiple independent anomalies, shape, emission pattern, pulsation timing, orbital behavior, align toward the same interpretation, rejecting it requires stronger justification than allegiance to familiar paradigms. Occam's razor favors the simplest explanation fitting all evidence. And for a growing number of researchers, that explanation involved intentional construction. A theoretical physicist proposed a thought experiment. Imagine humanity sending an interstellar probe powered by photon-based propulsion to explore nearby star systems. How would we design such a craft? We would likely adopt a regular geometry for structural stability. We would use multiple redundant emitters to prevent catastrophic failure. We would implement phase control for beam steering. We would synchronize emission with precise timing hardware. The resulting architecture would resemble 3I Atlas remarkably closely. This similarity between an optimal hypothetical human design and the observed characteristics of the object did not prove artificial origin, but it significantly increased its Bayesian likelihood. When an unknown object matches what independent engineers would design to solve similar challenges, the resemblance carries weight. The principle of convergent design suggests that optimal engineering solutions tend to repeat across contexts, regardless of the intelligence producing them. Philosophers of science entered the discussion, reviewing criteria for distinguishing technological artifacts from natural objects. On Earth, artifacts are typically identified by specified complexity, organized patterns that also fulfill an external functional specification. A clock is clearly artificial because its ordered intricacy serves the purpose of timekeeping. A naturally formed crystal can be orderly and complex, but it does not meet functional criteria associated with intent. iAtlas posed a unique problem because it showed both complexity and plausible functional specification if interpreted as a photon-propelled craft. The hexagonal frame provided structural complexity. The coordinated pulsations created temporal complexity. The correlation between geometry and emission points suggested a functional role. Together, these traits matched several proposed criteria for identifying technological artifacts. The question shifted from, "Is this natural?" toward, "What specific function could this configuration serve?" Engineers began building functional models showing how a system with the observed properties could operate as a propulsion or communication array. These models did not prove 3I Atlas was artificial, but they demonstrated that its characteristics aligned cleanly with plausible engineered architectures, strengthening the case for taking the unconventional hypothesis seriously. Part 5. Theories of Artificial Origin and Scientific Debate. The international scientific community found itself split in a way few had ever witnessed. What began as routine monitoring of an interstellar visitor had transformed into an existential dispute about the nature of 3I Atlas and the implications of its possibly technological origin. Conference halls at major observatories, academic forums, and scientific journals turned into intellectual battlegrounds where long-standing paradigms were openly challenged. Professor Avi Loeb, an astrophysicist at Harvard, known for his willingness to embrace provocative ideas about extraterrestrial technology, became one of the first prominent scientists to argue publicly that the evidence pointed toward an artificial origin. During a press briefing that drew global attention, Loeb outlined what he called the cumulative parsimony argument. Each anomaly in 3I Atlas could be explained individually through unknown natural processes, but taken together, the precise hexagonal geometry, coherent blue emission, exact pulsation timings, non-gravitational trajectory, and complete absence of comet-like signatures, they converge toward a single, simpler explanation: deliberate design. When we look at the pyramids in Egypt, Loeb said, we don't invoke exotic geological processes to explain their regular geometry. We recognize design because the organized complexity is statistically improbable without intention. Atlas displays comparable organized improbability. An honest application of Occam's razor suggests we're looking at technology. His position triggered intense reactions. Dr. Amaya Moro-Martin, an astrophysicist at the Space Telescope Science Institute, led the opposition, arguing that the alien artifact hypothesis violated fundamental methodological principles. Extraordinary claims require extraordinary evidence, she wrote in a Nature rebuttal. What we have is unusual evidence, yes, but not extraordinary in the sense of being unambiguous. Astronomy's history is full of mysteries that later received natural explanations. She emphasized that science progresses by formulating natural hypotheses first and testing them rigorously, not by leaping to intelligent agency when the responsible agents have never been observed. To her, 3I Atlas likely represented a previously unknown class of interstellar object with unique properties shaped by exotic formation conditions. The universe is more inventive than we are. Natural processes we haven't imagined yet can produce phenomena our limited experience fails to predict. The debate escalated when Dr. Michio Kaku, theoretical physicist at the City University of New York and a well-known science communicator, entered the conversation. He argued that excessive skepticism can be just as unscientific as gullibility. We've spent decades searching for extraterrestrial intelligence, Kaku noted in a widely circulated interview. Now that we might have found something, some colleagues insist it must be natural, no matter how improbable the required natural explanations might be. That's not scientific skepticism. That's psychological denial. Kaku proposed a Bayesian framework to assess the competing hypotheses. Before the appearance of 3I Atlas, the prior probability of encountering an alien artifact was low but non-zero, given estimates about technological civilizations and their capability to launch interstellar probes. The anomalies exhibited by 3I Atlas, he argued, should update those priors according to Bayes' theorem. If the observed properties are 1,000 times more likely under the artifact hypothesis than under a natural hypothesis, then our confidence in an artificial origin should increase proportionally, even if we begin skeptical. Critics countered that assigning numerical probabilities was arbitrary, since humanity lacked data on the frequency of alien artifacts or the range of exotic interstellar objects. Dr. Paul Davies, astrobiologist at Arizona State University, struck a middle position. We must take the artifact hypothesis seriously enough to investigate it thoroughly, but we must also maintain rigorous evidential standards. The burden of proof remains with those claiming artificial origin. The International Astronomical Union convened a special panel of experts to assess the evidence and attempt to form a consensus. The panel consisted of 20 astronomers, astrophysicists, and planetary scientists from institutions across 12 countries. They met virtually for weeks, examining every available data set. The discussions were intense, with opinions spanning the full spectrum, from near certainty of natural origin to high probability of technological construction. The final report, released in December 2025, reflected deep division. Most members agreed that 3I Atlas displayed highly anomalous properties that challenge conventional natural explanations. Yet they remained split on whether those anomalies justified an artificial origin conclusion. The report presented three formal positions: a natural interpretation, supported by 40%, an artificial origin interpretation, 30%, and an agnostic view, acknowledging insufficient data for any definitive conclusion, 30%. The natural origin defenders proposed speculative scenarios. One suggested exotic ice crystals formed under extreme pressure inside the cores of frozen exoplanets, later flung into interstellar space by catastrophic impacts. Such crystals could, in theory, exhibit unusual optical behavior and geometric regularity. Another scenario envisioned aggregates of interstellar dust grains shaped by electromagnetic fields inside molecular clouds, producing a structure with partial symmetry. These ideas faced criticism for being ad hoc and lacking observational or experimental precedent. Critics pointed out that although the scenarios did not violate fundamental physical laws, they required chains of highly improbable conditions tantamount to fine-tuning. Dr. Seth Shostak of the SETI Institute remarked, "We can always invent hypothetical natural processes to explain any observation, but at some point, parsimony favors the simpler answer. Someone made it." Engineers supporting the artificial hypothesis developed increasingly detailed functional models. A joint team of aerospace specialists from NASA, ESA, and JAXA collaborated on a conceptual design study built around a simple question. If we wanted to build a photon-driven interstellar probe using known physics and assuming technology more advanced than our own, what would it look like? The resulting design resembled 3I Atlas to an uncanny degree. A lightweight hexagonal frame for structural rigidity, multiple photonic emitters for redundancy and vector control, solar to optical, energy conversion systems, and a distributed thermal architecture. This convergence between an optimal theoretical design and the observed characteristics offered circumstantial yet persuasive evidence. Engineers noted that convergent evolution of optimal designs is a recognized principle. Different civilizations solving the same engineering problem under the same physical constraints should arrive at similar solutions. The streamlined bodies of fish, ichthyosaurs, and dolphins all converged because hydrodynamics imposed identical limits. Likewise, a photon-propelled interstellar craft might naturally evolve toward a narrow range of architectures dictated by fundamental physics. Philosophers of science joined the discussion, examining epistemic criteria for identifying artifacts. Dr. Carol Cleland of the University of Colorado argued that identifying an artifact requires detecting specified functional complexity, patterns that are both statistically complex and functionally aligned with independently recognizable purposes. A clock exhibits specified functional complexity because its ordered architecture fulfills the function of timekeeping. A crystal exhibits complexity, but not functional specification. 3I Atlas, she argued, met both criteria if interpreted as a photon-propelled craft. Its precise geometry and coordinated pulsations embodied structural and temporal complexity, while their alignment with photonic propulsion requirements supplied functional specification. "We are not anthropomorphizing ambiguous patterns," Cleland wrote. "We're recognizing a match between observed structure and hypothetical function that can be derived independently from physical principles." Philosophical skeptics countered that recognizing function presupposes prior knowledge of the designers and their intentions. "We identify clocks as artifacts because we know the humans who build them. Without any experience of alien technology," they argued, "we lack the contextual grounding needed to reliably distinguish artifacts from exotic natural objects." NASA astrobiology historian Stephen Dick wrote, "We may be projecting our own categories of design onto a natural phenomenon that follows organizational principles we do not yet understand." The debate also acquired sociological and psychological dimensions. Surveys indicated that younger scientists and those working in interdisciplinary fields, astrobiology, aerospace engineering, were more receptive to the artifact hypothesis, while older generations of traditional astronomers tended to be more skeptical. Psychologists suggested this reflected differing levels of investment in established paradigms and varying openness to revolutionary shifts in understanding. Anthropologist Catherine Denning, a SETI specialist at York University, noted parallels with earlier scientific upheavals triggered by unfamiliar phenomena. "When quasars were discovered in the 1960s, she observed, some suggested they might be artificial because their luminosity was inexplicable. It took years of observations and theory building before they were understood as active galactic nuclei. We are in an analogous phase with 3I Atlas. We know it is anomalous, but we do not yet know what it is." Theologians and humanists added perspectives on the cultural meaning of a potential confirmation of extraterrestrial technology. Father José Funes of the Vatican Observatory wrote that the discovery of alien intelligence would be compatible with theological views about the diversity of creation. "If the universe is so vast," he reflected, "it would be consistent that it contains a diversity of intelligent beings. Encountering cosmic brothers and sisters would broaden our understanding of humanity's place in creation without contradicting fundamental truths." Others emphasized existential philosophical consequences, learning that humanity was not alone, that other intelligences had arisen and achieved interstellar capability, would challenge long-standing assumptions about human singularity. Narratives about a unique human destiny would require revision. At the same time, confirmation that civilizations can survive long enough to develop interstellar technology would offer hope that existential filters, nuclear conflict, ecological collapse, uncontrolled technological runaway, can indeed be navigated. Economists and futurists speculated about practical societal impacts. Confirmation of alien technology could accelerate scientific investment and space exploration, echoing the technological boom of the Cold War space race. Alternatively, it could provoke anxiety about Earth's vulnerability to potentially superior civilizations, reshaping security policy and international cooperation. Meanwhile, observation campaigns intensified. Every major telescope on Earth and in space devoted precious time to studying 3I Atlas while it remained visible, before retreating into interstellar darkness. Proposals for dedicated interception missions multiplied, though realistic development timelines made it improbable that any could launch before the object moved beyond feasible reach. Scientific data continued to accumulate, clarifying details but rarely resolving ambiguities. The blue radiance remained enigmatic, consistent with photonic propulsion systems, yet lacking direct evidence of technological components. The hexagonal geometry challenged natural formation, though not to the point of absolute impossibility. The orbital deviations hinted at active control but could, in principle, arise from radiation pressure acting on an exotic geometry. The emerging consensus, if it could be called that, was that 3I Atlas occupied an epistemic gray zone, anomalous enough to justify serious consideration of an artificial origin, but insufficiently characterized for a definitive conclusion. This ambiguity frustrated many researchers, but reflected the reality of science confronting a genuinely unprecedented phenomenon. The 3I Atlas experience transformed strategies for searching for extraterrestrial intelligence. Traditional SETI programs had focused almost exclusively on intentional electromagnetic signals, radio or laser transmissions sent deliberately. The blue luminosity demonstrated that technosignatures might manifest instead as anomalous physical behavior of astronomical objects. This insight spurred new search protocols targeting deviations from purely gravitational physics, non-gravitational accelerations, unusual emissions, improbable geometries. The Vera Rubin Observatory, beginning full operations in 2026, incorporated algorithms specifically designed to identify 3I Atlas-like objects in its vast sky survey. Its first years uncovered dozens of interstellar visitors, yet none exhibited comparable anomalies, underscoring just how extraordinary 3I Atlas truly was. Part 6. Data from the James Webb Space Telescope and ALMA. The James Webb Space Telescope, modern astronomy's $10 billion technological crown, redirected its gold-coated beryllium mirrors toward 3I Atlas, with an urgency driven equally by scientific excitement and unprecedented public pressure. Observation time committees, which normally plan months in advance with meticulous deliberation, approved emergency proposals within hours. The scientific community understood that this might be the only opportunity in generations to study such an extraordinary object using state-of-the-art instrumentation. Webb's first observations began on 11 November 2025. Barely 24 hours after the initial detection of the blue radiance. NIRCam, a camera primarily designed to capture primordial galaxies through cosmic dust, now focused its exceptional angular resolution capabilities on a much closer, yet equally enigmatic target. The resulting images delivered views of the object with a clarity that astonished even veteran astronomers long accustomed to celestial wonders. Webb's angular resolution, limited only by diffraction in its 6.5-meter primary mirror, reached roughly 50 milliarcseconds at near-infrared wavelengths. At 3I Atlas's distance during the observations, around 50 million kilometers from Earth, this translated into the ability to resolve features roughly 12 meters across on the object's surface. For the first time, individual structural features, smaller than the object's total size, emerged with crystal clarity. The images revealed that 3I Atlas's surface was not uniform, but displayed complex patterns of reflectivity. Most of the area between the 6 hexagonal vertices exhibited a relatively homogeneous dark gray tone, with a reflectivity of about 20%, resembling carbonaceous materials or weathered basalt. Yet superimposed on this dark background appeared thin, linear structures linking the vertices, forming a hexagonal network of elements brighter and more reflective than the surrounding surface. These linear elements measured roughly 5 to 8 meters in width according to Webb's photometric data, right at the telescope's resolution limit, but still distinct enough for analysis. Their spectral reflectivity showed unusual behavior, They preferentially reflected light in the near-infrared, while absorbing more efficiently in the visible. This selective spectral response resembled engineered materials designed with tailored optical properties, not natural rock or ice, which typically exhibit more uniform reflectivity across the visible and near-infrared spectra. The 6 vertices of the hexagon appeared in Webb's images as complex, morphologically distinct structures. Each vertex consisted of a central circular region about 25 to 30 meters in diameter, significantly brighter than surrounding surfaces during periods of active blue emission. Encircling these bright central regions were concentric rings of alternating reflectivity, bright zones separated by darker zones, in a pattern reminiscent of Fresnel structures used in optics to focus or collimate light through interference. The resemblance between the observed vertex morphology and known terrestrial optical devices did not go unnoticed by optical engineers reviewing the images. Fresnel lenses use concentric rings with carefully shaped phase profiles to manipulate light wavefronts, achieving the functions of traditional lenses with dramatically reduced thickness and mass. Such structures are standard in applications requiring minimal weight, including lighthouses, compact magnifiers, and space-based optical systems. If 3I Atlas's vertices incorporated Fresnel-like structures, this would imply the ability to focus or collimate the internally generated blue light before emission into space. Such capability would enable narrow, directionally controlled beams rather than diffuse omnidirectional output, maximizing propulsive efficiency by concentrating photons along desired vectors. Optical engineering calculations showed that Fresnel lenses of the observed dimensions could theoretically produce beams with angular divergences of only a few degrees, sufficient for efficient photonic propulsion. Webb's near-spec instrument captured extremely high-resolution spectra from distinct regions of 3I Atlas, enabling spatially resolved spectroscopic mapping. This revealed subtle spectral differences between vertices. 5 of the 6 exhibited nearly identical spectra, with a primary emission line at 452.0 nanometers, their widths and fine structure indistinguishable within measurement error. However, the 6th vertex, designated Vertex F by researchers, displayed a slightly shifted main line at 452.3 nanometers, just 0.3 of a nanometer longer. This spectral offset from a single vertex triggered intense analysis. One possibility was that Vertex F experienced slightly different physical conditions, temperature, pressure, or altered composition, modifying its emission. Alternatively, the shift could arise from Doppler effects, if that vertex moved with a marginally different velocity due to rotation or structural vibration. A third, more speculative interpretation was that Vertex F might be operating in a slightly different functional mode or experiencing partial degradation after prolonged activity. The variability of one emitter among 6 suggested both standardization, 5 identical, and tolerance for deviation, one slightly different yet functional, a pattern consistent with engineered redundant systems where partial component degradation does not compromise overall performance. In high-reliability engineering, architectures with multiple redundant subsystems ensure continued operation even under localized failure, precisely the pattern the observations hinted at. Mid-infrared observations with the MIRI instrument provided complementary thermal data. Operating between 5 and 28 micrometers, MIRI is sensitive to thermal emission from objects with temperatures ranging from about 100 to 1000 Kelvin. The measurements showed that 3I Atlas's surface temperature distribution was highly non-uniform. The vertex regions reached peak temperatures of roughly 1800 Kelvin during periods of maximum emission, while the areas between vertices remained far cooler, around 300 to 400 Kelvin. Such a pronounced spatial thermal contrast, a factor of 5 in temperature between regions separated by only a few hundred meters, was difficult to reconcile with a high conductivity material like solid rock, which would rapidly redistribute heat toward equilibrium. The observed variation implied effective thermal insulation between hot and cold regions, possibly through low conductivity materials, internal vacuum gaps, or intentionally engineered barriers. Such thermal architecture would be optimal for a system where localized heat generators, the emitters, must remain hot for efficient operation, while surrounding surfaces act as radiators shedding excess heat into space. MIRI also detected faint infrared spectral features attributable to molecular vibrations of silicates and possibly metal oxides. These signatures suggested that at least some surfaces contained mineral materials resembling rock or ceramics. Their elevated temperatures, far above simple radiative equilibrium, implied internal energy transport from generation sites, likely solar absorption zones, toward the emitters via conduction or convection through internal structural elements. While Webb observed from its orbit around the L2 Lagrange point 1.5 million kilometers from Earth, the Atacama Large Millimeter Submillimeter Array in Chile complemented these measurements with millimeter and submillimeter data. With its 66 antennas spread across baselines up to 16 kilometers in the Chilean desert, ALMA functions as a giant interferometer, delivering angular resolution comparable to Webb, but at vastly longer wavelengths. ALMA's observations near 230 GHz, 1.3 millimeter wavelength, provided crucial information on large-scale structure and thermal properties. At millimeter wavelengths, ALMA detects thermal emission from cold dust and surface materials, probing regions that might appear obscured or blended in infrared observations. The data revealed that 3I Atlas exhibited a millimeter brightness temperature of roughly 200 Kelvin, consistent with a body absorbing and re-emitting solar radiation thermally at the observed heliocentric distance. However, the spatial distribution of millimeter emission was not uniform. ALMA's aperture synthesis imaging showed that the regions between vertices were brighter at millimeter wavelengths than the vertices themselves. This inversion, vertices bright in optical near-infrared yet faint in millimeters, with intervertex regions showing the opposite, suggested fundamentally different emissivity properties across the surface. Radiative transfer physicists interpreted the patterns as evidence of spectrally selective surfaces, materials whose emissivity changes dramatically with wavelength. The vertices appeared to have high emissivity in the optical, efficiently emitting blue light, but low emissivity in the millimeter regime, behaving like reflective or metallic surfaces. The intervertex regions showed the opposite pattern: low emissivity in the optical, but high emissivity in the millimeter range, acting as efficient far-infrared radiators, yet poor visible light emitters. This specialization, different surface regions optimized for different thermal and optical functions, matched precisely what engineers would design for a spacecraft with complex thermal management requirements. Optical emitters optimized for a specific wavelength, thermal radiators optimized for far-infrared cooling, and potentially solar absorbers optimized for visible/UV energy capture. The inferred thermal architecture resembled that of advanced terrestrial satellites. ALMA also conducted line spectroscopy in frequency bands where molecules such as water, carbon monoxide, methanol, and more complex organic species exhibit characteristic rotational transitions. These searches were extraordinarily sensitive, capable of detecting molecular abundances at parts per million levels if a gaseous coma surrounded the object. The results were largely negative, No spectral lines from common cometary volatiles were detected, placing upper limits on gas production rates of less than 100 grams per second. For context, a typical comet at 0.3 astronomical units from the Sun would sublimate vigorously at hundreds to thousands of kilograms per second, producing a large coma, easily detected via molecular lines. The near-total absence of outgassing from 3I Atlas, despite extreme solar proximity, was inconsistent with volatile, rich cometary composition. This implied a surface composed of refractory materials, rock, metals, ceramics, capable of withstanding high temperatures without significant vaporization. However, ALMA did detect a weak but statistically significant carbon monoxide emission line corresponding to the J=2:1 rotational transition at 230.538 GHz. The line intensity indicated a CO production rate of roughly 50 grams per second, tiny compared to comets, but detectable with ALMA's sensitivity. This suggested that even largely refractory materials could contain trace volatiles trapped within mineral matrices, released slowly via solar heating. Doppler measurements of the CO line showed the gas expanding at about half a kilometer per second, typical of thermal sublimation. Yet ALMA's spatial imaging revealed that the CO did not emerge uniformly across the surface, but from specific regions that did not correlate with the luminous vertices. This asymmetric outgassing could contribute to non-gravitational forces through a small rocket effect, though calculations showed that the observed CO flux was too low by a factor of 100 to account for the measured non-gravitational acceleration. Photonic propulsion had to be the dominant mechanism. Combined observations from Webb and ALMA produced a complementary dataset spanning ultraviolet to millimeter wavelengths, forming an unprecedented multispectral portrait of 3I Atlas. The emerging image was of an object with a sophisticated surface architecture optimized for specific functions: solar energy capture, conversion into coherent blue light, directional emission via optical structures, and thermal management through specialized radiators. Every observed feature fit coherently within a functional model of a photonic propulsion system, while natural explanations required multiple improbable coincidences. Part 7. The Photon Engine Hypothesis and Engineering Analysis. Aerospace engineers and propulsion physicists, working through the growing body of data on 3I Atlas, began constructing detailed technical models of how a photonic propulsion system could operate using the object's observed characteristics. This reverse engineering effort was not meant to prove that the object was artificial. Instead, its goal was to show that the properties matched a plausible technology grounded in known physics, significantly strengthening the credibility of the technological hypothesis. The fundamental idea behind photonic propulsion rests on physical principles understood since the early 20th century. Photons, although they have no rest mass, carry linear momentum equal to their energy divided by the speed of light. When a system emits photons directionally, it experiences recoil in the opposite direction to conserve total momentum, just as a rocket gains thrust by expelling hot gases. The key difference is that photons travel at light speed, the fastest possible speed in the universe, maximizing the conversion of energy into momentum. The core equation for photon thrust is surprisingly simple. The generated force equals the emitted luminous power divided by the speed of light. For 3I Atlas, with an observed blue light power output of roughly 10 trillion watts, the theoretical thrust reached about 333 newtons. This value, derived directly from observations without adjustable parameters, matched remarkably well with the thrust required to explain the independently measured non-gravitational acceleration from precision astrometry. To frame this magnitude, 330 newtons corresponds to the weight of about 73 pounds under Earth gravity, compared to the millions of newtons produced by chemical rocket engines. It might appear negligible, but the essential advantage of a photon engine lies in its ability to operate continuously for extended periods without consuming meaningful amounts of propellant. Chemical rockets deliver immense thrust, but exhaust their fuel within minutes or hours. Photon engines generate modest thrust, yet can run indefinitely as long as a sufficient power source exists. Momentum balance calculations showed that if 3I Atlas had a mass of roughly 3 million kilograms, an estimate based on observed size and an inferred density consistent with a mostly hollow structure, then 330 newtons of continuous thrust would yield an acceleration of 0.00011 meters per second squared. This figure aligned almost exactly with the measured non-gravitational acceleration of 0.0001 meters per second squared. The quantitative match between theoretical prediction and independent measurement provided remarkably strong validation of the photon engine model. Operating continuously for a full Earth year, such acceleration would change the object's speed by about 3.5 kilometers per second. Over decades of operation, velocity changes could accumulate to tens or even hundreds of kilometers per second, sufficient for major orbital adjustments, planetary flyby maneuvers, inter-system target changes, or long-term interstellar trajectory. Modifications enabling visits to multiple stars over journeys lasting millions of years. Energy analysis highlighted the elegance of the inferred design. At a distance of 0.3 astronomical units from the Sun, the solar flux is roughly 11 times stronger than at Earth, delivering about 15,000 watts per square meter. An object with a solar collection area of 50,000 square meters, reasonable for a hexagonal structure about 300 meters across, would intercept roughly 750 megawatts of solar power. If the system converted that solar energy to electricity with 20% efficiency, comparable to advanced silicon or gallium arsenide photovoltaic technology, it would yield about 150 megawatts of electrical power. If that electricity were then converted to blue light with 60% efficiency, similar to state-of-the-art solid-state LEDs, the system would produce 90 megawatts of coherent blue emission. Observations, however, indicated a luminous output near 100 terawatts, implying that the energy assumptions or area assumptions required adjustment, or that the effective solar collection area was significantly larger than initially estimated. Recomputing using the observed light output of 10 trillion watts and assuming an overall solar-to-optical conversion efficiency of 10%, the system would require capturing a full petawatt of sunlight. At 15,000 watts per square meter, this would necessitate an effective collection area of about 65,000 square meters. A hexagon with a vertex-to-vertex width of 350 meters has an area of roughly 90,000 square meters, easily sufficient to meet the energy requirements with comfortable margins. The agreement between the independently calculated energy requirements and the physically observed scale of the object provided yet another layer of validation. The object was neither inexplicably small nor unreasonably large. It was almost exactly the size required to generate the observed power via plausible solar collection. Such correspondence is exactly what one expects from engineered systems, where dimensions follow functional requirements, not from natural objects, whose sizes result from random accretion or fragmentation. A 6-emitter hexagonal configuration offered several engineering benefits that human designers immediately recognized. First, it provided redundancy. If one or two emitters failed during a journey spanning millions of years, the remaining units could continue operating at reduced capacity, but without system collapse. This fault-tolerant philosophy is fundamental in space systems where repair is impossible. Second, a distributed multi-emitter arrangement enabled vector control of thrust without rotating the entire object. By adjusting the power output of selected emitters, the system could generate a net thrust component in any desired direction within the plane of the hexagon. For example, boosting the output of 3 adjacent emitters while lowering the opposite ones would shift the net thrust vector toward the reinforced side. This allowed full triaxial control without moving parts, offering far greater reliability than gimbaled engines or reaction wheels, which depend on mechanical actuators susceptible to wear. Third, the spatial separation of the emitters facilitated distributed thermal management. Each emitter produced significant heat as an unavoidable byproduct of imperfect energy conversion. Spreading them around the perimeter prevented heat concentration that could melt materials or degrade efficiency. The regions between emitters could act as thermal radiators, shedding excess heat into space through far infrared emission, precisely the behavior observed in thermal data from Webb and ALMA. The sequential activation pattern, clockwise sweeping with each emitter firing every 20 milliseconds, served multiple engineering purposes. First, it distributed thermal load temporally as well as spatially, giving each emitter roughly 80 milliseconds of rest between active cycles. This 20% duty cycle reduced peak operating temperature, extending material lifespan and improving system reliability. Second, the sequential activation created net angular momentum that could be used for attitude control. When an emitter turned on, it produced not only linear photon thrust, but also torque about the object's center of mass if the emission axis didn't pass exactly through it. By firing emitters sequentially around the perimeter, these individual torques added vectorially, producing controlled rotation. By adjusting the relative duration of each activation phase, the system could modulate rotation rate or even reverse it, enabling full orientation control without expending propellant. Third, the sweeping pattern allowed each emitter to operate in high peak pulsed mode rather than at a lower continuous power level. Many laser and coherent emission systems achieve higher efficiency in pulsed regimes, where high instantaneous intensities favor nonlinear processes that improve energy conversion or beam coherence. The pulsed behavior, seen in 3I Atlas, may not be a limitation, but a deliberate optimization. Optical engineers analyzed the Fresnel-like structures observed at the vertices, modeling how they could function as collimating elements to concentrate internally generated blue light into narrow beams. Electromagnetic wave simulations showed that concentric rings with appropriate spacing and depth could focus light through constructive and destructive interference, producing beams with angular divergence as small as 2 to 3 degrees. Such tight collimation would maximize propulsive efficiency in 2 ways. First, concentrating photons into a narrow cone ensured that most of their momentum contributed to thrust, rather than radiating isotropically. Second, the system could steer beams in specific directions by varying the relative phases of the emitters, achieving electronic beam steering without mechanical components. For an interstellar probe requiring continuous trajectory adjustments over millions of years, this capability would be invaluable. The specific blue wavelength, 452 nanometers, also had potential technical significance. This band lies in a region where the interstellar medium, its tenuous gas and dust, produces comparatively low absorption. Ultraviolet wavelengths are strongly absorbed by atomic hydrogen. Infrared wavelengths scatter efficiently off dust grains. Blue visible light strikes an optimal balance, energetic enough to carry substantial momentum per photon, yet long enough to traverse interstellar space with minimal attenuation. Additionally, 452 nanometers corresponds closely to electronic transitions in wide bandgap semiconductors, such as gallium nitride, the material used in modern blue LEDs. If the emission system was based on an LED-like technology at macro scale, the selection of 452 nanometers could reflect fundamental properties of optimized emitter materials. This speculative interpretation suggested that the builders of 3I Atlas, if they existed, had converged on solutions similar to those independently developed by human civilization, indicating that physical laws drive technological evolution toward similar outcomes. The materials required to survive such extreme operating conditions posed challenges familiar to terrestrial engineers, but not yet solved at human scale. Emitters operating at gigawatt powers would experience thermal flux densities of megawatts per square meter, enough to vaporize most known materials within seconds. Only specialized refractory ceramics, such as silicon carbide, hafnium carbide, boron nitride, or more exotic composites, could endure such environments. These materials would also need to retain mechanical and optical properties across thermal cycles of thousands of degrees, repeated millions or billions of times over spans of millions of years. Thermal fatigue gradually degrades materials through repeated expansion and contraction. Designing a system capable of surviving such cycles without catastrophic failure would require extraordinary materials engineering, possibly involving self-healing structures or architectures that tolerate cumulative damage. The weak but organized magnetic field detected by Juno provided further clues to internal architecture. Localized magnetic dipoles at the vertices suggested substantial electrical currents flowing through defined circuits. If each emitter operated at 10 to 20 gigawatts with operating voltages in the kilovolt range, the required currents would reach millions of amperes. Such currents naturally produce magnetic fields under Ampere's law, exactly as observed. Electrical engineers recognize this as the signature of pulsed, high-energy power systems, analogous to capacitor banks that store electrical energy and release it in intense bursts. In a photonic propulsion system, solar energy harvested continuously could be stored in superconducting capacitors or electromagnetic flywheels during charge phases, then discharged in synchronized pulses to drive the emitters. This architecture would explain both the pulsed emission and the associated magnetic fields. The observed dependence on solar proximity suggested an intriguing mission strategy. The blue emission activated only when 3I Atlas reached roughly 0.4 astronomical units from the Sun and intensified as it approached closer. This implied that the system required a minimum solar flux to operate, perhaps because photovoltaic converters needed to exceed resistive losses, or because energy storage systems required a minimum charging rate. This solar dependence defined an elegant operational cycle. The probe would remain inactive during interstellar transit, where starlight is negligible, conserving resources and minimizing wear. As it approached a star, rising energy flux would gradually activate its systems. Near perihelion, it would operate at peak capacity, performing trajectory maneuvers while also exploiting the star's gravitational assist. As it receded, activity would taper off until it returned to interstellar hibernation. This hybrid strategy, combining active propulsion with passive gravitational assists, maximized exploration efficiency. Stars served simultaneously as renewable power sources and gravitational slingshots, allowing a probe to visit multiple stellar systems over extended timescales. Trajectory calculations showed that velocity increments of only a few kilometers per second per stellar encounter could enable chained flybys of many nearby stars, permitting exploration of dozens of systems over millions of years. The implications for the prevalence of technological civilizations were profound. If 3I Atlas represented a functioning interstellar probe, this demonstrated that at least one civilization had reached the capability to project physical presence across interstellar distances. The existence of such capability implied a civilization that endured long enough to develop interstellar technology and that devoted significant resources to exploration rather than succumbing to self-destructive conflict or ecological collapse. Part 8. Cultural Legacy and the Future of the Search for Extraterrestrial Intelligence. The blue glow of 3I Atlas faded gradually as the object moved away from the Sun, crossing the orbit of Mars in December 2025 and heading into the depths of the outer solar system. By late January 2026, the luminous emission had weakened beyond detection even for the most powerful telescopes, and the interstellar visitor returned to the dark, silent state in which it had entered the solar system months earlier. But although the blue light vanished from the sky, its impact on human consciousness and the direction of science endured, transforming how humanity sought and conceptualized extraterrestrial intelligence. The final observations made by the Hubble Space Telescope in February 2026, when 3I Atlas was already beyond Jupiter's orbit, showed that it had fully reverted to its inactive state. No glow, no anomalous thermal output, only a faint point of reflected sunlight consistent with a rocky object of its size. The transformation from brilliant blue emitter to dark pebble reinforced the interpretation that the system had been temporarily activated by solar proximity and had now re-entered hibernation for its long voyage through interstellar space. Astronomers calculated that 3I Atlas would continue on its hyperbolic path away from the Sun at about 30 kilometers per second, modified slightly by the photonic acceleration it experienced during its active phase. It would cross the heliopause, the boundary where the solar wind yields to the interstellar medium, around the year 2030, reaching distances comparable to the Voyager probes after 4 decades of travel. By mid-century, it would be hundreds of astronomical units away, far beyond any realistic hope of observation or interception with foreseeable human technology. The scientific legacy of the encounter appeared immediately in the transformation of extraterrestrial intelligence search programs. For more than 60 years, since Frank Drake's first SETI experiment in 1960, searches for alien civilizations had focused almost exclusively on electromagnetic signals, intentional radio or laser transmissions. The blue glow demonstrated that technosignatures could manifest in completely different ways, as anomalous physical behavior of astronomical objects previously overlooked until careful observation revealed features incompatible with natural processes. This realization energized the emerging field of interstellar artifact searches, sometimes called SETA, Search for Extraterrestrial Artifacts. In contrast to traditional SETI, the Vera Rubin Observatory, which began full operations in 2026, implemented detection protocols designed specifically to identify objects with properties similar to 3I Atlas. The algorithms no longer looked only for interstellar trajectories, but also for anomalous emissions, periodic brightness variations, non-gravitational motion, improbably regular geometries, and spectra inconsistent with known natural materials. The first 5 years of Rubin operations detected about 40 additional interstellar visitors, validating predictions that such objects passed through the solar system regularly but had gone unnoticed before wide-field survey telescopes existed. Of these 40, 38 showed all characteristics of ordinary asteroids or comets, differing only in their hyperbolic orbits. One object was extremely elongated, similar to Oumuamua, the first interstellar object detected in 2017, but showed no anomalous emission. Only one, designated 4I/2028S1 and informally called Echo, exhibited anomalies, provoking speculation about artificial origin. Echo showed modest non-gravitational acceleration without detectable outgassing and an approximately octahedral geometry, but no active emission remotely comparable to the blue glow of 3I Atlas. The debate over Echo remained unresolved, illustrating both how exceptional 3I Atlas had been and how difficult it was to define objective criteria distinguishing artifacts from exotic natural bodies. Global space agencies responded to the 3I Atlas encounter by beginning serious planning for interception missions. The European Space Agency proposed a mission concept called the Rapid Interceptor, a spacecraft kept in Earth orbit on high readiness, capable of launch within weeks of detecting an incoming interstellar object. Using advanced chemical propulsion and optimized trajectories, the interceptor could achieve solar escape speeds of 50 kilometers per second, enough to intercept many objects during their passage through the inner solar system. NASA developed a complementary concept called Extended Encounter, a spacecraft with solar electric or nuclear electric propulsion that, once it reached the target, could adjust its trajectory to accompany the object for months, performing detailed, close-range observations. Such a mission would require years of transit, but would deliver scientific returns far superior to distant telescopic observations. Preliminary budgets were in the multi-billion-dollar range, comparable to flagship planetary missions like Cassini or Mars Sample Return. However, political and budgetary realities kept both missions at the conceptual stage for years. Funding competed with missions to Mars, Europa, Titan, and other traditional targets with well-defined objectives. Intercepting interstellar objects remained a gamble, expensive and technologically demanding, and potentially unrewarding if the target turned out to be a perfectly ordinary rock. Only the detection of another object as anomalous as 3I Atlas could justify the required investment. The cultural impact of the blue glow rivaled its scientific significance. Unlike previous interstellar detections that primarily interested professional astronomers, 3I Atlas captured global public imagination. The blue light, visible even in amateur images, made possible alien technology feel tangible and accessible. Videos of real-time pulsations spread widely across social media, accumulating hundreds of millions of views. Public opinion surveys in 20 countries in December 2025 showed dramatic increases in acceptance of extraterrestrial intelligence. Before the blue glow, about 40% of respondents in Western countries considered intelligent alien life likely somewhere in the universe. After the encounter, that number rose to 65%. More significantly, the share of respondents who considered it plausible that extraterrestrial intelligence had visited the solar system rose from 15% to 40%, reflecting the impact of having a concrete candidate rather than abstract speculation. Philosophers and theologians contemplated profound existential implications. Jesuit priest José Funes, director of the Vatican Observatory, wrote a widely read essay arguing that extraterrestrial intelligence was compatible with Christian theology and could enrich understanding of divine creativity. If God chose to fill the cosmos with diverse, intelligent creatures, he wrote, it reveals a generosity and abundance of divine love beyond what anthropocentric theology imagined. Secular humanist thinkers emphasize different themes. Oxford philosopher Nick Bostrom suggested that if 3I Atlas represented a probe from a civilization that had endured for millions of years, the timescale required for interstellar travel at sublight speeds, then this offered hope that existential threats facing emerging civilizations like humanity could be navigated successfully. The existence of ancient, technologically advanced civilizations suggests that self-inflicted catastrophes, nuclear war, ecological collapse, are not inevitable, Bostrom argued. Some civilizations find the wisdom to survive their technological adolescence. Artists and cultural creators found renewed inspiration in the real encounter with possible alien technology. Films, novels, music, and visual art experienced a surge of creativity. Unlike earlier science fiction focused on communicative or invasive aliens, much of the post-Atlas cultural output explored ambiguity and the mystery of silent artifacts whose nature and purpose remained opaque. This reflected the reality of the encounter. Humanity may have detected alien technology, but understood little about its makers, intentions, or journey. Educators reported an explosive rise in student interest in science, technology, engineering, and mathematics. Enrollment in astrophysics, aerospace engineering, and astrobiology programs rose by 30 to 40% over the following years. Science policy leaders recognized an opportunity to revitalize investment in STEM education and fundamental research, arguing that the next generation needed preparation for an era in which encounters with extraterrestrial intelligence might shift from speculation to reality. However, the encounter also generated anxieties and debates about planetary security. Some commentators worried that if extraterrestrial civilizations sent exploratory probes across the galaxy, more ambitious visitors of unknown intent might eventually follow. This perspective fueled calls to develop planetary defense capabilities, not only against hazardous asteroids, but also against potential artificial threats. Though most scientists viewed such concerns as premature, given that 3I Atlas displayed no sign of hostility or even awareness of Earth. International protocols for responding to extraterrestrial intelligence encounters, developed by the International Academy of Astronautics over previous decades, were updated to incorporate lessons from 3I Atlas. The new guidelines emphasized open scientific data sharing, honest public communication about uncertainties, and avoidance of unilateral actions. The consensus was that humanity must respond collectively to possible extraterrestrial encounters, not as competing nations, but as a unified species. Astrobiologists broadened their search strategies. Traditionally, the field focused on microbial life in Mars or icy moons, or atmospheric chemical signatures of biological metabolism on exoplanets. The blue glow demonstrated that technological intelligence could be detectable, even without intentional communication. This inspired proposals to search for passive technosignatures, industrial atmospheric pollutants on exoplanets, megastructures altering stellar light curves, or anomalous emissions from transiting objects. The Breakthrough Listen program expanded its scope to include optical monitoring of transients alongside traditional radio searches. New dedicated telescopes scanned the sky continuously for brief optical flashes, possible photonic propulsion signatures, interstellar spacecraft braking burns, laser communications, or unknown technological transients. Planetary scientists reflected on how easily 3I Atlas might have gone unnoticed. A slightly different trajectory, one that never brought it close to the Sun, would have produced no blue glow at all. Decades earlier, with weaker survey capabilities, it might have passed through entirely undetected. These reflections underscored how many potentially meaningful interstellar visitors might have crossed the solar system throughout history without recognition. This realization motivated investment in improved tracking systems. The proposed Interstellar Sentinel project envisioned a network of small, space-based telescopes distributed across the inner solar system, offering continuous, all-sky coverage and sensitivity to fast-moving, faint objects. Such a system could detect interstellar visitors weeks or months earlier, enabling coordinated observations or even interception attempts if an object displayed sufficiently intriguing properties. Historians of science placed the blue glow within a longer sequence of paradigm-shifting discoveries. Galileo's moons of Jupiter showed Earth was not the center of all celestial motion. Hubble's discovery of galaxies revealed a vastly larger universe. Exoplanet detections in the 1990s demonstrated that planetary systems were common. The blue glow of 3I Atlas potentially represented the next step: recognition that humanity was not alone as a technological species in the cosmos. Yet historians also cautioned against premature certainty. Astronomy's history included many cases where phenomena initially interpreted as possibly artificial turned out to be natural. The canals of Mars, pulsars, early fast radio bursts. Scientific caution required remaining open-minded about 3I Atlas, even as accumulating evidence leaned toward a technological interpretation. Decades later, in the 2060s, historians would look back on the blue glow as a hinge moment, when humanity shifted from passively waiting for alien messages to realizing that extraterrestrial artifacts might pass through the solar system regularly, requiring only careful observation and an open mind to recognize them. Educational programs would teach the event as an example of scientific progress. Meticulous observation, rigorous debate, and a willingness to consider paradigm-challenging possibilities when justified by evidence. The ultimate legacy of the blue glow may have resided not in the answers it provided, but in the questions it raised. Who built 3I Atlas, if anyone? How long had it traveled, and how many star systems had it visited before arriving here? Was it still executing a mission programmed millions of years ago, or was it a derelict relic of a long-extinct civilization? Did it carry records of its creators, messages for future civilizations, or simply instruments gathering data on interstellar conditions? These questions remained unanswered as humanity watched 3I Atlas disappear into interstellar darkness, carrying its secrets to unknown destinations among the stars. But the questions themselves permanently reshaped human awareness, expanding horizons of possibility and reminding humanity that the cosmos might contain wonders and mysteries beyond even the boldest imaginations of science fiction. The blue glow had faded, but its metaphorical light continued, illuminating the search for understanding humanity's place in a universe potentially filled with innumerable intelligences, each exploring, questioning, and marveling at the vastness and mystery of creation.